refer. There you go. Did I hit the beep? Oh, okay. Well, you know, you never know. All right. I will begin with a word of prayer. I see we're starting 3 minutes late. My apologies. I'll go 3 minutes over to make up for it, though. So, only 3, yeah. Okay, that's debatable. All right. Lord Jesus, we thank you for this day, and thank you for the students. Just ask you to bless our work today. Help us to glorify you what we do, and just understand a little bit more about your creation together, Lord. In your name I pray, Lord Jesus. Amen. So, all right. So, just to let you guys know, like, what I'm trying to do is to write notes for myself every class that kind of like frame my lecturing, which isn't to say that I'm just writing those things down on the board verbatim. Like, sometimes I'm just writing these notes in the interest of getting certain things out of my system so that I don't end up saying them in class, you know? But anyway, other times if I'm tired, I might project the notes, but I'll try not to do that for the most part. Are there any questions before I show you some more examples and stuff? No? All right. Yes?
So in the homework, there was part of it that referenced something such as A cross grad. Grad? Yeah, where grad is graded. Or downward.
A cross grad? Well, that would just be the cross product of A with the vector field. That's the gradient. So like, all A cross grad would mean? Are you talking about like grad of something? Or just like that?
Yeah, just like that. But then there's something afterwards too.
What question?
You'd have to, be more specific. I don't know, like, what are you talking about? Like,
I think it's 161E. We can do it another time.
it's okay. I just don't know.
I have not gotten there yet.
There's problem four.
What page is that?
It's question 1.61, so it's like later on.
It's at the very end of chapter 1.
I'll come back to it.
I'm like question 4.
I saw the it showed up there. I was like, oh, wait on that one.
Or about it's the last one.
Yeah, F.
And I was like, I'll let him
Let him cook. Let him cook.
Already on like 8 pages.
Jesse, let him cook.
So your question is on how to interpret integral of dA vector cross nabla cross v vector.
Yep. Just expand on that commercial.
Yeah, I don't know right offhand. I'll have to work that one out, you know. I haven't run across that, so I'd have to like work the rest of the problem to understand the context of that notation. I mean, I could hazard a guess, but I don't think that if I write down what I'm thinking, it's going to be helpful to you. So yeah, I'm gonna punt on that for now. But, well, yeah. Other questions? Easier questions? Yeah.
This is sort of like a logistical one. It says this is worth 37 plus 3 points. Does that just mean there's like an extra there?
There's an extra 3 points to earn, because I have like 37, 37, 37, 38, 38, 38 or something like that in order to get the points to add up to 1,000, because as you know, but I like 40 points for this set. So that means there's 3 bonus points, which are, in some sense, it's a license to skip part of the homework, like, for example, 161 part F. But anyway. All right, so I'm trying to post the lectures that I'm, like these handwritten lectures. I was trying to scan them and put them on the website. So we'll be able to find them there. I haven't scanned this or posted it yet, but that's where I'm heading to. All right, so I want to show you an example. And this is kind of an example of examples, but I think it's interesting. So we're going to look at the sphere of radius r and positively oriented, right? So like the dA is outward, right? So our dA is r squared sine theta d theta d phi r hat. All right. And I want to calculate, I want to consider the flux of the vector field F equals to r to the power n times r hat. I want to consider this vector field. I want to calculate the flux of that particular vector field through the sphere. I'm leaving n as a variable. All right? Does that make sense? So let's do it. So the integral of F, the flux of this vector field through the sphere of radius r, is equal to the integral from 0 to 2 pi, the integral from 0 to pi of my F, which is r to the n. And now I should be careful here. When we're doing the surface integral, we're doing what? We're evaluating the vector field at the sphere. So the equation for this is simply little r equals to big R, right? So when I calculate the surface integral, I put big R to the n, r hat. That's my F evaluated at the surface. And then I take the dot product with the dA, which in here is r squared sine theta d phi r hat. Do you guys feel hot in this building? No, it's just me.
Sometimes.
Yeah, okay. Interesting. Okay, so what happens then, of course, is r hat dot r hat is what? It's 1. And lo and behold, we have r to the n plus 2, times integral from 0 to 2 pi of d phi, and integral from 0 to pi of sine theta d theta. This gives me a 2 pi. This works out to 2. Lo and behold, we have 4 pi r to the n plus 2. Right. Now, how about the divergence of F? I'd like to do the same calculation, but use the divergence theorem, right? So what's the divergence of F? Well, if you look at your handy-dandy formula sheet that I gave you, and if your eyesight's better than mine, you can see it's 1 over r squared partial r of r squared F sub r, right? Plus other stuff with f sub theta and f sub phi, both of which are 0, right? So like the other two terms in the divergence need not concern us here, because those involve the theta and the phi component of this vector field, of which there is none. So in this case, we've just got 1 over r squared partial r of r squared. What is the r component? F sub r is what, by the way? If you want a formula for it, it's f dot r hat, right? If in doubt about how to calculate the component with respect to a variable, you take the dot product of the vector field with the variable's unit vector. That picks off the component in that direction. So of course, here, it's just r to the n, right? And so what we have is 1 over r squared. That gives me n plus 2, so I have n plus 2, right? R to the n plus 1, right? So when I differentiate r to the n plus 2, I get n plus 2 times r to the n plus 1. And then by the usual algebra, we've got n plus 2 times what? R to the, n minus 1. Right. So continuing then, if we calculate the integral over the ball of radius r of the divergence of f, so this is my notation. B sub r is the ball of radius r centered at the origin. S sub r is the sphere of radius r centered at the origin, and I'm going to try to keep using those. Yeah.
Does tau always refer to volume element?
Tau is the volume element in Griffiths and also in my board work. As much as I can, I'm trying to stick with Griffiths notation. All right. Okay, so this is apparently the integral from 0 to r, integral from 0 to pi, integral from 0 to 2 pi. The divergence is n plus 2, r to the n minus 1. But what is d tau? Remember, d tau in sphericals is r squared sine theta in d theta, d phi, d whatever order. I'll put them in the right order to match the bounds down here, but you got yourself r squared sine theta. Let's see here. I did d phi first, I did d theta second, and I did d look at that. Look at that. See what that is?
I think that's an R. Looks like an R to me.
Right.
R. dr. Okay, I feel better. Now, of course, we need to simplify this. This gives us, let me just write out here. So we have integral from 0 to r, r to the what? R to the n plus 1. Dr, integral from 0 to pi. You know what? Forget all this. 4 pi. All right. The angular stuff integrates to 4 pi. It's the same stupid integral again. This integrates to what? R to the n plus 2 divided by n plus 2, 0 to r. Oh, I was about to say, this doesn't match. What's wrong? Yeah, okay, well, thank you. Hey, look at that. They'd be canceling. So, yay. This is just equal to, r to the n plus 2. And of course, you're about to complain, but I'm going to beat you to it, 4 pi. So I got 4 pi, r to the n plus 2, minus 0, right? So what do you guys think?
Does n mean anything? Or is just a replicator?
N is I'm assuming n is like an integer here. Like n equals to 0, plus or minus 1, plus or minus 2.
As long as you don't have n equal like -3.
Ah,
Because then
right.
evaluate r at 0.
So, very good. N equals to minus 3, problem. Problematic, right? In fact, n plus 2 less than 0 is trouble. Right? This integral blows up in that case. Right? And the same for that one. In fact, well, okay, so how about this? There's something very special here that happens, right? If we have n equals to minus 2, we get that the flux of this vector field is what? Four pi, right? That's the example I did last class. The Coulomb field. N equals minus 2 is the Coulomb field here, the unit Coulomb field. I multiplied it by like a q over 4 pi epsilon, q over epsilon not last time, but it's the same mathematics. But what I want to show you is like the only case that the flux is independent of the radius is n equals minus 2. Like that only happens for the like reciprocal square law. And what's the deal with n equals to minus 2 though over here? So first of all, as Sam noticed, if n if n is less than minus 2, for one thing, this whole calculation just breaks down at the origin. If n is equal to minus 2, this works out for pi, that's fine. But this over here doesn't work out at all when n equals minus 2. Because you have division by 0, right? And of course, well, as we pointed out last time, the divergence of f, right? The divergence of, if you will, r hat over r squared, right, is actually equal to, 1 over r squared partial r of r squared times the r component. R component here is 1 over r squared. So that's equal to 1 over r squared partial r of 1, right, which is equal to 0. But don't be deceived. This is only true where there is some fine print here, right? This is assuming r is not equal to what? Right, r not equal to 0. Okay? But, so Griffiths has the following quote. He says, "We found the divergence of r hat over r squared is 0 everywhere except the origin. And yet, its integral over any volume containing the origin is 4 pi." Let me read that sentence again. "The divergence of r hat over r squared is 0 everywhere except the origin, and yet its integral over any volume containing the origin is 4 pi. What does he mean by that, right? How do you integrate? So what he means by that, right, guys, is that the integral of, r hat over r squared, right, dot dA over the sphere of radius r, right? This is known to be 4 pi. We just calculated it. All right? And what Griffiths is saying is that what's basic to him is that the divergence theorem is true. So this has to be equal to, you see, the divergence of r hat over r squared times d tau over br. Notice that SR is equal to the boundary of the ball. The sphere of radius r is the boundary, outward oriented boundary of the ball. How does that work? How can you have something integrate that's 0 everywhere except for 1 point, integrate to 4 pi?
Do we have to incorporate the Dirac somewhere?
That's right. The Dirac Delta function is what has to come into play in order to make Griffith's dream a reality. Because this dream is pure nonsense if you're thinking about it from Calc 3. From a Calc 3 perspective, you simply cannot apply the divergence theorem here because it does not apply. Because this vector field is divergent. You see, not vector, this function is divergent at the origin. Like, what we need, right, is that the divergence of r hat over r squared is equal to 0 for r not equal to 0, right? And infinity for r equals to 0. No. But I hear you. Okay, so we're going to get back to that, but that's the problem. That's what we need to address. And to do that, we need to talk about the Dirac Delta function. And so rather than jumping straight to the three-dimensional case, I think I've motivated, I hope, the three-dimensional case, but let's talk about the one-dimensional Dirac Delta, right? So it's technically not a function. It's actually, I'm going to say Dirac Delta device because it's not a function. It's a device. And here's the definition in one dimension. Delta of x, it's 0 if x is not equal to 0, and it's infinity if x is equal to 0. Now that doesn't really, I say that's a definition, but that's not really the definition. The definition operationally is more like this. For any function, on R, the integral from minus infinity to infinity of f of x times delta of x minus x naught dx is equal to f of x naught. So I always tell differential equations that the Dirac delta function turns integration into evaluation. So all you do is you just plug in the value of this at the point, and that's how you define it. So, example, if I was, say, integrating from minus infinity to infinity of 3 plus x squared delta function of x minus 1 dx, what would this work out to? So when is the delta function is 0 everywhere except x equals to 1, all right? And so this, we just have to evaluate that at 1, so we get 3 plus 1 squared. So the answer here would be 4. Now technically speaking, we can build the Dirac delta function from like a sequence of functions which has the properties that we want. Like basically, you can think of it essentially as like a sequence of like tent functions like this, where every one of those has area 1 under this tent. All right, so like it gets more and more steep, but every one of these has area 1, and you take the limit as it gets steeper and steeper and steeper, you always have area 1 under every triangle, and that is what you would rigorously build the delta function from, like a sequence of functions, every one of these having area 1 under the tent, letting the tent go to 0, yet always having area 1 under increasingly taller pyramids. So when you take that and you multiply that by a function, the resulting area, the triangles just get multiplied by f of x naught, and then the area is not just 1, it's 1 times f of x naught, which is why this is working like it is. But these kinds of thoughts don't help you at all with this course. Let's go on. So, yeah.
Would you always have to integrate from negative to infinity, or just an interval that contains 0? Or that contains whatever?
Well, we consider integrals from minus infinity to infinity, but if you have an integral from 2 to 3, you can just as well extend it from minus infinity to infinity. It's still the same integral because it's 0 everywhere except for where it's not. Now, that would cease being true if the delta was, if you're integrating, all right, now you're dragging me into a discussion of measure theory. So if you're integrating from 2 to 3, like a delta function that's infinite at 1, right? I think the answer would just be 0. You have to give meaning to that. Like these delta functions are defined in terms of integrals from minus infinity to infinity. So what you're asking me to do is to extend the definition to other contexts, which I'm not willing to do. Sorry. But I think the answer would be 0. So this kind of is a guide for the question you're asking. You can just use that intuitively. But yeah.
So if over there it has an equals 1 is 0, then it shouldn't be like something times infinity? Or am I like not thinking it right?
Here?
Like over there. Yeah.
No, but look what's happening. When we integrate f of x times the delta function, we don't get infinity, right? We just get,
Point.
we plug in the point. That's it. That's the definition. That's all I'm doing here. X naught is equal to 1. My f of x in this context was 3 plus x squared. So definition, d1 and d2 are equal delta functions. All right, provided the integral from minus infinity to infinity f of x d1 of x dx is equal to the integral from minus infinity to infinity of f of x d2 of x dx for all, as Griffith says, ordinary functions. f of x, all right. All right, so like example 3. So I'll work through something he works through. And once you have this example, you can solve the homework problems like super easy. So let's go through it, make sure we're understanding. So, and I'm going to assume we're going to show that delta of kx is actually equal to 1 over k times delta of x. All right? At no point are we going to be doing arithmetic with infinity. So if you're thinking about that, stop. This is a workaround. Okay, so if we integrate 1 over k delta x times f of x dx, what do we get? For any function, like the 1 over k pulls out, and we just get 1 over k times f of 0, right? All right. On the flip side, what if we integrate minus infinity to infinity of delta of kx times f of x dx? All right, and we're going to assume k is positive here, okay? Just to make it simpler to follow. Now, so what we do is just make a u equals kx substitution. I think he does y in the book. I'll go with y. Try to follow him. Y equals to kx, all right? So then that means that like y of 0, excuse me, y of, blah, 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 I'll eventually get it, guys. So y of plus or minus infinity is still equal to plus or minus infinity, right? Because k times plus or minus infinity is still plus or minus infinity because k is positive. What I'm trying to say is under this change of variables, the bounds don't change. So the bounds, they're still minus infinity to infinity in the same order. And then, of course, we have delta of y, f of what?
Y divided by k.
Y divided by k, right? And then, let's see here. You guys know the drill. dy is k dx. So that means that dx is dy over k. All right? And so what that gives us is integral from minus infinity to infinity. I'll bring the 1 over k out front. Delta of y, f of y over k, dy. And then applying the definition of the delta function, is something I wrote wrong? Definition of the delta function, I get 1 over k times f of 0 over k, also known as 1 over k f of 0, right? But this calculation holds for arbitrary functions, right? See, this, that, they be matching. Consequently, by the definition of equality of delta functions, this is equal to that. Yep.
So because you used the chain rule, you assumed that the Dirac Delta is continuous, or at least differentiable.
I assume that the chain rule holds in this context. The truth is that's probably part of the definition of the delta function if we were to really work it out. But admittedly, I have not developed the mathematical background to justify said step, nor am I willing to, because this is not a course in measure theory, which is where such things have to be proved. Because there you just study the full theory of distributions and have a way of saying these kinds of things. Ask Shane. Right? No?
I know that.
Yes. So example 4, let's just put, okay, so by the way, generally speaking, delta of kx is actually equal to 1 over the absolute value of k times delta of x. That's like what happens if k is negative. You just add 1 over absolute value, as it turns out. Because the bounds, they be flipping, but you also get the minus from the, anyway, that happens. So, for example, if I am integrating minus infinity to infinity of like, I don't know, x squared plus 7 delta of 2x dx, that is just equal integral from minus infinity to infinity of, we bring the 2 out, x squared plus 7 over 2 delta of x dx. And there you go. We're off to the races, right? So 7 halves. All right. If I teach this course again, odds are very high I don't go through this particular calculation I just went with you guys through. But anyway, there it is. All right, so how about higher dimensional deltas, right? What about the delta function in 3 dimensions? How does that work? So here is the definition in 3 dimensions. Well, actually, I'll just do it in n dimensions. Why not? So if you integrate over Rn, a function of n variables times the n-dimensional delta of r minus r naught, well, guess what? Over the n volume. Care to guess what you get? I heard an f of r sub naught, and I would say correct. So in the 3-dimensional context, we use d tau, and we get, again, f of r0. This is the, and what this means, like, intuitively, is that delta sub n, not sub, but upper n, of r minus r naught, right? It's equal to 0 if r is not equal to r naught, and it's equal to infinity if r is equal to r naught. But that infinity is an infinity that is set up in such a way that when we do the n integral, we get a n volume of 1 if we're just integrating the delta function alone. But if we multiply the delta function by a function, then we pick up the value of the function at said point where the delta function's infinity, and yet has a n volume of 1 there. So example, and this is the example, the most important example of today for sure. Is that we could write rho of r is equal to q times direct 3-dimensional direct delta function of r minus r naught. This is a very important function. Here rho is meant to be dq dv. This is the so-called charge density, right? And what I'm telling you is that q times the 3-dimensional direct delta function is the natural charge density function for a point charge at r naught. And if we all right, so like, there's more I was going to tell you. So if we're integrating over a volume, right, dq, that would be the charge enclosed, right? the charge enclosed in a volume V would be the integral of dq. But to do that, we actually integrate rho of r, right, times d tau in our notation, right? I might write dv there in a moment of weakness, but anyway, the volume. But this is the integral over v of q, three-dimensional Dirac delta, of r minus r naught d tau. And what's that equal to? It's either equal to 0 if r naught is not an element of the volume, or it's equal to q if r naught is an element of the volume. And that's just a mathematical formulation of what we mean by point charge. The delta function is the mathematics of a point charge, right? All right. So notice then that if we calculate the integral of r hat over r squared, I keep losing my place. Rather, the divergence of this guy, right, over a volume. How's that work out? Right. So he wants to say, well, this is what Griffiths wants to say. He wants to say this is 0 if, you know, if 0 is not an element of V, right? But Griffiths wants us to say it's 4 pi if 0 is an element of V, right? Because Griffiths is assuming that this has to be equal to the boundary of V, you know, r hat over r squared dot dA, which, by the way, is equal to 4 pi. You're like, wait a minute, but I don't know that's a sphere. Well, I would remind you, in Calculus 3, we learned a deformation theorem, which says that if V looks like this, and inside V, the origin is here, if the divergence of the vector field is equal to 0 between here and there, it is true that the integral over the R sphere inside here is equal to the integral over V, boundary V rather, because you can, there's a version of the divergence theorem which allows for holes inside, and if you apply that theorem, it says that the flux through the inside has to be equal to the flux through the outside, provided that the divergence between the two is 0, which is just a fancy way of saying that if the divergence is 0 between S sub r and boundary V, then the flux through S sub r has to be equal to the flux through the boundary V. But r hat over r hat over r squared is the function that's divergence is 0 everywhere. We calculated that today. So you see, if 0 is in there, if 0 is inside a volume, then you can look at the little ball around 0, and you can deform the integral over the boundary of the volume to that little bubble, and you can get the 4 pi by our calculation, right? But again, this is Griffith's wishful thinking that Calculus 3 holds there, right? But if you put this all together, you see what we should say. Which delta function, I mean, what do we need to get to the point here? So what we have to say then, to make this all work together, is that the divergence of r hat over r squared is actually equal to what? 4 pi what? 4 pi delta 3 of r. Indeedly doodly. That is the secret sauce to get Griffith's wishes. This repairs, in Griffith's language, this repairs the divergence theorem for the Coulomb field. Rather than saying the density is not defined at the origin like we would in calculus 3, we say the density is defined by the Dirac Delta function, and once we do that, we still get the divergence theorem. We still get to say that the integral of the flux is equal to the volume over the boundary is equal to the volume integral of the divergence, which is the divergence theorem. So anyway, that's and so you see that this Dirac delta function and this Dirac delta function, these are equal because if you integrate it over three-dimensional functions, if you put a function here or if you put a function here, in either case you still end up with the function at 0 times 4 pi. So they have the same distribution. Yeah.
Can we achieve the same result using the limit definition of divergence?
Oh no. Well, I mean, you might. I can't today. But is it possible to obtain these things with limits? Yes, but I mean there is a workaround, in fact, of delta functions. If you don't want to use delta functions, we can play the game that I was starting to play last week, and we can just always like look at. We can never actually consider the origin. We always just encircle the divergence with a little bubble. And then you work between the little bubble and the surface you're interested in. And by doing regular calculus 3 between the bubble and the surface and taking the limit as the bubble goes to 0, yes, you can recover these results. That is true. But this is much, much cleaner to use the Dirac delta function. Because it just gives us like straight calculational. Well, let me show you a calculation that uses these things. The takeaway message here, guys, is you need to know the divergence of the inverse square, like r hat over r squared, is 4 pi delta 3 of r. We will need that. And I do think you get to explore these things a little bit more in the homework, right? So, yeah. All right. Let me try to be quick on this example here. So this is example 1.16 from Griffiths. And in here, he shows us how to calculate, he calls it J, the integral over a volume. And the volume is the ball of radius r. And what he's doing is he's integrating r squared plus 2 times the times the divergence of r hat over r squared d tau. All right. So the first way to do this integral is the way you should do it. All right. The way we should do this integral is to use what we just learned, which is that the divergence of the unit Coulomb field is what? It's just 4 pi three-dimensional Dirac delta of r. So this is equal to 0 squared plus 2 times 4 pi, also known as 8 pi. Game over. We're done. All right? But not being content with that, Griffiths wants to illustrate some of the calculus involved by instead calculating this by an integration by parts. You might ask why. I don't know why, but I do think it's actually a nice calculation because you get to see some different divergences and gradients and things. It's a nice calculation. So I'll start out by showing you the divergence of r squared plus 2 times r hat over r squared, all right? So look at this. This is a product of a function times a vector field. In your homework, you proved the product rule for divergences, yes? Have courage. These things still work for infinitely divergent fields. So, yeah, I know. I know, it gives me pause as well, but let's just follow follow the yellow brick road. Let's see here. R squared plus a 2. And then dotted with r hat. So I just did the divergence rule. It's the first things times the divergence of the vector field plus the gradient of the function dotted with the vector field. That was the product rule for divergences that you proved in the homework, or you will soon prove. Prove is the wrong word. You'll derive. There we go. All right, so the thing is that this is equal, well, let me just save myself from writing. This works out to 2r times the gradient of r, and that is 2r times, what's the gradient of r? R hat. If the gradient of x is x hat, the gradient of r should be r hat. It's a linear coordinate. But you could calculate it too if you wanted. But it is r hat, that's right. So this, if you solve, gives us that r squared plus 2 times the admittedly divergence of r hat over r squared should be equal to what? So I'm solving the product rule above for this, yeah? So what do we get? We get the divergence of r squared plus 2 times r hat over r squared minus, when we calculate the dot product of the gradient with that, what do we get? The r hat dot r hat gives me 1. I get 2 over r squared, so that just simplifies to minus 2 over r, all right? So J is equal to the integral over the ball of radius r of divergence of r squared plus 2 times r hat over r squared minus 2 over r. Now he calls this integration by parts, right? Because he doesn't write what he didn't write this down in the Griffiths. I'm just showing you what he's doing. He's using the product rule for divergence to rewrite the integral as what? So this first piece, by the divergence theorem, is the integral over the boundary of the r ball, right? Of r squared plus 2 r squared plus 2 times r hat over r squared. All right. That's by the divergence theorem. And then minus the integral over the r ball of 2 over r d tau. But details, this is the integral over, 0 to pi, 0 to 2 pi, and we've got, r squared plus 2 over big R squared. And my bad, I'm supposed to have a dot what here? Dot dA vector, right? But the dA vector for the boundary of the R ball is what? It's r squared sine theta. My current order would be d phi d theta. So, and then minus the integral from 0 to r, integrate from 0 to pi, integrate from 0 to 2 pi. Why did I do it in that order? Who knows? 2 over r. And then the spherical volume element, remember, is r squared sine theta. Current ordering of variables d phi, d theta, dr. Small victories. I didn't do rho this time. All right. And so that gives us, this piece gives me a r squared plus 2, same integral again, times 4 pi. And then minus, well, this ends up giving us a 4 pi r squared. All right, I'll just cut through the noise. This integrates to 4 pi r squared because you get just a 2r here, which integrates to r squared, which little r squared, which when you evaluate gives you a big r squared, and this thing still integrates to 4 pi. As you can see, the 4 pi r squareds, they be canceling, and we get 8 pi. Now, I don't know about you, but I like that way. But I show you this calculation because you get to see some things along the way, like here's a way we can use the product rule for the divergence to do what's called integration by parts, right? We can trade a given volume integral for a different volume integral paired with a surface integral, you know? Yeah. All right, so that brings us to the final story arc for today, which is the Helmholtz theorem. All right. And so the Helmholtz theorem, which I guess I should probably write out. Let me see how much time I don't have. Oh, we're good, actually. I may yet actually end on time. Who knows? Wait a minute. When does class end? I was thinking 5:20. Oh, man. So I'm already a minute over. Let me use the projector then. So the Helmholtz theorem is at the tail end of chapter 1, and what it tells us is that a vector field can be written as the sum of a gradient and a curl if we have sufficient conditions on the vector field. The sufficient conditions on the vector field are that the gradient, that the I maybe needed the divergence, not the, sorry guys, it's the gradient. Give me a second here. What's that? Oh yeah, that's fine, that's fine. I'll get it. Thank you. I'm about to show my Calc 3 notes where I have the Helmholtz theorem proved in terms of the bubble stuff that Shane was tempting me to talk about. Yeah. This is the part of Calc 3 that I only cover if I have a very strong class, because otherwise it's pure insanity.
What percentage of your classes are very strong?
We're talking about maybe half, maybe one in 3.
Imagine top hat.
But you need a top hat, right?
Wait, do we have to do top hat?
Well, you don't have to, but it would be nice if. Anyway, the join code is 660-210, and 9022 is the one for today. All right, and again, I don't really care if you don't, but so in my Calc 3 notes, which I will post on my website and other things, at the very end, I talk about Green's identities in the Helmholtz theorem. Now, the problem that Shane was asking me about, the evil 1.61 part F, is somewhat connected to this discussion. In fact, I think that problem's asking you to work through these. These are easy, actually, by the way. These are not bad.
Yeah, that's the previous 2 parts.
Yeah, that's not bad. So these are Green's first and second identities, which are, oh, the double scrolling, it's got me. No, what in the world? Just don't do that to me, you stupid computer. All right, I do up-down arrows. That should be safe. So Green's second and first identities, and then you get these theorems. Let me get straight to the point here. We don't have much time. And this is Green's third identity. Green's third identity, and then this is this lemma that involves taking the limit as the radius goes to 0 of a little sphere, and you go through these rather laborious arguments that essentially. This is the Dirac Delta function done carefully without doing distributions is what's going on here, okay? Anyway, it leads us to Helmholtz's theorem. Helmholtz's theorem says that if you have a vector field, this is really all I want to tell you. You have a vector field for which the divergence is given to be a function d, and the curl is given to be a function f. And if that's the case, if you know that the vector field goes to 0 as r goes to infinity, and also, if the C and the D, all right, if the curl and the divergence of the vector field go to 0 faster than the inverse square of the radius, then F is uniquely given as the sum of a gradient and a curl. And not just that, the potential function and the vector potential can be calculated by simply calculating these integrals. The interpretation, this has application. This is the voltage from the electric field, actually. And this ends up, there should be a vector here, ends up actually matching what we'll call the vector potential for the magnetic field. So like the mathematical basis for what we do in here, it kind of all rests on Helmholtz's theorem, truth be told. That said, if you don't know Helmholtz's theorem, you'll probably be fine in here. It's just, it's part of like a larger, if you ask certain mathematical questions, they're mostly answered right here. So, anyway.
B and C are necessarily
Orthogonal. I don't say that. But are they? But D is a scalar function, and C is a vector.
or maybe
I think it's... Anyway, I'm sure I'll circle back to this. If you go past this point in my notes, I show how this derives all of the major theorems in this course in terms of like electric field, magnetic field, and its interplay with the scalar potential and vector potential. But hey, we haven't gotten to that yet in here, so let me stop that. Yeah.